I want to write this out as an ionic equation. As a total ionic equation. And who can tell me what that would look like? Let me ask you, when I say an ionic equation, how is that going to be different than just the chemical equation that's written there? Yep. Good. So is that going to affect our solid zinc? What do you think? Right? Well, if we're talking about an ionic equation, does solid zinc involve any ions? No, no ions in solid zinc. What about copper sulfate? Aqueous, so it involves ions. So I'll do the left side for you, and you can do the right side. Solid zinc is just solid zinc, and we should write it as such. But copper sulfate is made up of two ions. Kendra Schaefer, what's one ion in copper sulfate? Copper. Hey, it doesn't tell us here, what are the two possible charges that copper can take? Does anyone remember? 1 and 2, good. Which one do we have here, and how do you know? Yes, we have the 2+. How does Mr. Castillo know, Zach Brown, that we have the 2+ ion here? Can I tell you, Mr. Brown? Not only are you right, and you are, but that was music to my ears. Very good. Was it really? I was gonna say if it was a guess, it was a very convincing sounding guess. He is good at music, so it only makes sense. All right, I'd like you to do the same for the right side of this reaction. Okay, I'm glad. No, that's good. You will. I'm glad. Look over. Yeah, that's beautiful. That's beautiful. Well done. Okay, so if we look here, on the right side of this equation, we have solid copper, and it is reacting with zinc ions. Mr. Castillo, what charge does zinc have? 2+, very good. And its state of matter, Mr. Marks? Very good. And Zach Brown? DSL Coda. What do I get here? Very good. What charge? Very good. And very good. Thank you. Now, we want to take that total ionic equation. And what that total ionic equation means, let's take a quick look at it, is it tells us in aqueous solution what's actually going on here. Because remember, when something is aqueous, if it's ionic, look at me, all your eyes looking at me, if it is ionic, when it's aqueous, it dissociates, it breaks into its various ionic parts. Do covalent compounds break apart? No. In fact, if you look, SO4 is a covalent ion, right? You could draw it if I asked. The S in the middle with 4 oxygens around it. It does not split into sulfur and 4 separate oxygens. Covalent bonds stay together in one, but ionic bonds associate. Does that make sense? So when an ionic compound is aqueous, it breaks up into its individual ions like this. Now below I've asked for the net ionic equation. What is the difference between a total ionic equation, which we made here, and a net ionic What thinkest thou? Yes, sir.
Everything that.
Good. So we could talk about what is consistent. Like I would look and say, okay, I've got zinc here and zinc there, right? Why not? The different states of matter, they have different charges, so I can't cancel that. Zach Brown, what can I cancel? Yeah, because that is the same on each side. What do we call those? The things that stay the same in a chemical reaction, that don't actually change. Anyone remember? They're the same things, that's right. It's been the same thing. Hey, if you go to a sporting event, what do you call all the people who aren't playing the sport? Very good. We call these the spectator ions, those ions lacking in audacity. As Zach Brown would have us understand, and I agree with that. They just aren't trying hard enough. All right, so then can somebody please tell me what my net ionic equation will be? What am I actually writing down below? Solid zinc. What charge does that have? Right? Very good. Now, let's take a good look at this reaction, because really, it's very telling. In this chemical equation, we take solid zinc, and what happens to that zinc? Focus just on the zinc for a minute. It changes state, so it goes from being solid to being aqueous. What else changes that? It has charge of 2+, which means it has lost two electrons. So zinc has lost 2 electrons. Where did those electrons go? Does that make sense? Now, why was zinc solid and it became aqueous? Well, because solid zinc has no charge. So it has no reason to be dissolved in water. Right? We know why things dissolve in water. It has to do with the polar nature of it. Right? One half that has a slightly positive charge, the other half has a slightly negative charge. Due to, why is that again? Why is water polar? Yeah, it's got a dipole. Yeah, specifically which means what? What is true about the hydrogen in the water? What's true about the oxygen in the water? That leads to us having a polar molecule. Good. The oxygen has a greater pull on electrons than hydrogen. We measure that using a measure called electronegativity. The oxygen is more electronegative. It has a pull on those electrons. So solid zinc has no reason to be dissolved because it has no charge. So it is neither attracted to the positive side of the water nor to the negative side of the water. The copper, on the other hand, because it was a charged ion, it has a positive charge. What side of the water molecule is it going to be attracted? Yep, the negative side, which is which side of it? Or both answers. So that's pretty non-committal. Which one is it? Oxygen, right? Because oxygen is more electronegative. Oxygen is an electron hog. Yeah, so here, the copper is attracted. But what's going to happen is zinc is going to give 2 electrons to copper. In so doing, copper now has no charge, which means it is no longer attracted to the water, which means it no longer has any reason to stay dissolved. It becomes a solid. But having given up 2 electrons, Zinc now has a positive 2 charge, and because it has a positive 2 charge, it is now attracted to the oxygen side of water. Does that make sense? That's what's actually happening in a single displacement reaction. So we said in grade 11 chemistry that it doesn't actually have anything to do with sulfate, and it doesn't. Sulfate is a spectator ion. We see now what it really has to do with is the valence electrons of zinc. Zinc gives up 2 valence electrons, and those are received by copper. That's the reaction. Does that make sense? The sulfate is just a taxi surface. All the sulfate is doing is, in its solid form, listen, that's a great question. The question is, why do we need sulfate? The answer is, I can't have solid copper ions. That wouldn't be stable. Does that make sense? So there's no such thing as having a pile in front of you of copper plus ions. Nothing, come on in, nothing with an electrical charge. Hello, come on in. Yep. Nothing with a positive or a negative charge can exist in big volumes without something to neutralize that charge. Does that make sense? That's one of the rules of nature. It doesn't like extremes. It doesn't like things that have positive charges. It doesn't like have things that have negative charges. And keep in mind, could you have a solid made up of a whole bunch of particles all with the same charge? What would those particles want to do to each other? What do like charges do? They repel. So are you ever going to get a clumped together solid of something with a plus charge? No. To get something to clump together and be a solid that I can stick in a jar, it has to be neutral. And so to get copper 2 plus ions, I need something to cancel out the 2 plus. All the sulfate is a way to stick it in a jar. Does that make sense? All the sulfate does is it allows the positive charge of the copper to be canceled by something. And once the positive charge of the copper has been given to the zinc, because the copper is stolen zinc electrons, now the sulfate is just canceling positive charge zinc. So its only purpose, it's just a taxi driver. It just allows this stuff to exist in one place. Does that make sense? No different than like, every school needs a building, but it's not the building that's doing any of the learning in the future, right? It's a place for it now. So when we say the sulfate's a spectator ion, it's almost more meaningful to talk about it as being like the stadium the game is played in, right? Like it's just a delivery surface. All right, so zinc atoms lose electrons to form zinc ions. Copper ions gain electrons. And if you look, I've written these as separate kind of reactions. Does that make sense? If you really look at this, 2 things happen. Solid zinc becomes ionic zinc, and ionic copper becomes solid copper. Those are the 2 things that happen. Now, we are scientists, and if there's one thing scientists like, it's to give things vaguely confusing names. So let me ask you a question. If you wanted to name gaining electrons, that type of reaction, a reaction where something gains electrons, what might you call it? A reduction. Actually kind of a weird choice to me, but it seems like somebody has read ahead. What might you call it? I might call it like something that most sort of negative, right? Because it takes a negative charge, or maybe like something called electron in it. You know, I might call them like electron gaining reactions. Think EGRs, that's kind of nice. And we could call the opposite electron losing reactions. ELOs. Wouldn't that be nice? Nice simple naming, right? But we don't. Instead, one of them we give a name that kind of makes sense. But don't worry. The other one we give a name that is just crazy. Like it makes no sense, right? And I'm not going to pretend it makes sense. Ready? So we give these 2 things names. When we lose electrons, we call that oxidation. Okay, Why do we call it oxidation? Does anyone know? Does anyone have a guess? We actually talked about oxygen a little earlier. And what's true about oxygen? Oxygen is it has a high electronegativity, which means electron likes to do what? Oxygen likes to do what to electrons? It likes to take them. So we call this an oxidation reaction because we first observed it by letting things interact with oxygen. Okay? If you put iron in the presence of lots of oxygen, it gets oxidized. It will give up electrons and become iron ions. Right? And that's rust. You end up with this flaky thing that isn't strong at all. Rust in particular is ionized iron that is stuck to ionized oxygen, called iron oxide. But oxidation happens often when you put something near oxygen, but there's the stupid part. Does oxidation have to include oxygen? No. Oxidation happens anytime an atom loses electrons. Atom loses electrons, we call that oxidation. Now, these reactions always have to happen in pairs, because if something is losing electrons, something else must be gaining. And the act of gaining those electrons we call reduction. Because its charge is being. Does that make sense? Because its charge is getting more and more negative. Having said that, yes, when we gain something, we call it reduction. I hate science. I mean, I love science. It's my passion. But you have to admit, that's some terrible naming. I actually can't decide which one.
Naming in science is terrible.
No, that's not true. Some of it's really good, like all of biology is pretty wonderful. It's very descriptive. They're Latin-based, which means that the language is non-specific. And if you speak Latin, they happen to be just like really, really, really exact on-the-nose descriptions of the thing in question. I think biology naming is great. Chemistry is a victim of its own history, because everything's named when it's discovered, and then 30 years later we know a lot more about it, and we understand it much more generally, but things still have the name from right at the beginning. Right? Except IUPAC, which they keep updating, which is a good decision. Now, so here's what we know. Anytime we do a reaction that involves electrons moving around, we call it an oxidation-reduction reaction. Now that's very long, so wouldn't it be nice to keep that a short form? So we tend to call them redox reactions. Read for reduction, ox for oxidation, redox reactions. And that's what this unit is all about. J-Bar, you need a note? Where did I put those? That's maybe all the questions.
Talking about somewhere. I can find it.
You go ahead. Okay, so all of that is a preamble to let's get into this, shall we? We shall. So, I want you to react lead with copper 2 nitrate. So I want lead to react with copper 2 nitrate. Draw that reaction for me. And then, once you've done that reaction, I want you to identify what thing is oxidized and what thing is reduced. So take a minute and write that reaction out. And I'm going to pull up here in case we need it. Because I got to be honest, I don't off the top of my head know what charge lead takes in an ionic compound.
More like two.
Yeah, it seems like the type of thing I would have done to pick something that works nicely. So I'm generous like that. There we go. I don't love that paragraph. That's my usual one. And yeah, you can go ahead and use the 2+ ion when it's time to do that, when it's appropriate. You must have been anytime we can chill out with you. All right, let's talk trade bar. I'm good. How are you? What's chemical symbol for symbol? What's the chemical symbol for lead? Flubber. For lead.
Oh, PD.
Very good. And if we're just talking about lead all by itself, what will its state of matter be? Yeah, definitely. It's a metal, right? All right, what are we reacting it with? Okay, so let's go over here. What's symbol for copper? Nitrate, do you remember it? It's very good. And do we remember what charge nitrate takes? We can look it up if we don't. My memory is that it's 1, but I don't always have good memory for stuff, so let's look it up. Nitrate is NO3 and it's -1. Okay. So NO3 -1. And what charge is our copper taking? Cool. So what's the formula for this thing going to be? Very good. All right. So SU NO3. All right. Yep. Which one? Yes.
Oh,
There you go. Good eye. No, listen, that's good. You knew exactly what you needed. Okay, now, what's the only type of reaction this can do? I suppose this could decompose, but...
The one where they switch.
Cool, so let's do it. What's now going to be by itself over here? Yeah. And, man, so if you're like me and you wrote this way too far to one side, what you should do is highlight it, and like slide it over, and maybe even shrink it a little tiny bit, just like that. That's better, right? Okay. Now we have solid copper by itself, and we'll have to do another little side note, because now what's going to be together? Lead and nitrate. We know nitrate's -1. And lead, I looked up on the periodic table of the ions, and it's 2+, so this is actually going to be very similar. It will be what? Very good. Nice. And these will both be aqueous, right? We're assuming. Okay, I've been working on this over here. How's that look compared to what you guys have? Okay. When we go to make this a net ionic equation, do I even need to put the total ionic equation step in the middle, or can we intuit this? What are going to be the spectators? Yeah, the NO3s are going to be spectator ions, right? So what will the net ionic equation of this thing look like? Solid lead? Yep. Copper ions, good. And what charge will those copper ions have? 2+, good. And again, why am I allowed to just not include the nitrate? Well, because, yeah, there's 2 nitrates on the left side. They're aqueous. They have a -1 charge. And on the right side, there's 2 nitrates, and they're aqueous, and they have a -1 charge. Are they actually reacting? No. What is over here, then? Solid copper. And Very good. What then can we learn from this? Well, let's talk about copper. What happens to it? It goes from aqueous to solid. Good. What else happens to it? Okay, so it loses its charge. It goes from 2+ to nothing. How is it going to lose charge? How's it going to go from being positive to being neutral? What must happen? That is one way of thinking that, actually. We'll talk about that later. But just in terms of what determines something's charge? How many?
Oh.
Right,
How
like
many things it gives away?
Yeah, if we imagine back in the day and we have our orbitals here, right? We've got all the electrons around. How many electrons it has, right? So if it went from having a +2 charge to having no charge, what must be true about it in terms of electrons? What happened to it? Became stable, for sure. It became stable by getting electrons or losing electrons. If it lost them, it should become more positive, right?
Yeah.
So it must have gained them. How many did it gain? Good. So this had to gain 2 electrons. That makes sense? Now, on the other hand, if we talk about lead, what happened to it? It went from being stable and solid, full shell, to having a +2 charge. What then must have happened to lead? It lost 2 electrons. Now, based on the naming above then, what can we say? If copper gained electrons, then we can say copper is what? Oxidized or reduced? Reduced. And on the other hand, if it lost 2 electrons, we can say that lead is oxidized. So to answer our original question, lead is oxidized, copper is reduced. Wow. Side note, the colors are nice on my screen, and they're kind of nice on that screen. They're not quite as nice, but it's pretty good. I wonder how it handles the green. That's the real test.
Oh, look, even like pull up the highlighter thing.
Like, that's pretty good.
Look, wait, you touch it, and then you can see all.
Yeah, that's amazing. All right. You know what? This is my new room. We're just going to install a sink and a fume hood, and this will be great.
These can already be the lab benches.
Yeah, we're
Just
good.
raise them a little.
Yeah, raise them up a bit. We're good. They need to be pneumatic, like on a coach bus, how it goes up and down. I want that for these, so I can be like, it's lab time, kids, and then press a button, and they go like, and they'd make that sound. It'd be pretty cool. All right, so here we have a reaction, and we are able to look and say that in this reaction, lead is oxidized because it loses electrons. Copper is reduced because it's gaining electrons. Okay, now how do we remember this? There are 2 mnemonic devices that we use to remember this. One of them is better than the other, and I'll let you decide which is which, but you better agree with me or you're wrong. Okay, which one am I going to do first? Okay, the first one is this. Oxidation is losing electrons. Reduction is gaining electrons. And thus, the mnemonic device that helps us remember this oil rig. In 20 years, when electric cars have taken over, you can explain to your children what an oil rig was. It was this thing we used to pump old dead plants and dinosaurs out of the ground so we could burn them. Weird, right? But that's, I got news for you. That's what it is. Actually, most oil, I believe, they believe was aquatic life, and coal was more mammalian life, as I understand it. Anyway, doesn't matter. So there we go. So that's one of the ways of remembering it. The other one is this. Lose electrons, oxidation. Gain electrons is reduction. And so, of course, in this case, Leo the lion says, grr. So in 20 years, when global warming has accelerated because we haven't adopted electric cars, you can explain to your children what lions were. Couldn't tell you. Anyway, whichever one you prefer is up to you, of course.
So which one was right?
Well, you tell me, which one's better?
The Leo Gur one's confusing. Gur's not a real word.
Yeah, so A, it's not real. Secondly, it involves nonsense syntax, right? Lose electrons, oxidation. Gain electrons, reduction. Those aren't sentences. Whereas oxidation is losing electrons, that's a sentence, kids. Reduction is gaining electrons. You can put a period on the end of that thing, because that, oh, that's a highlighter. Because that's also a sentence. So clearly oil rig is superior because it's syntactically natural. Anyway. Now. The one thing I don't want you to think is we've done the easiest ways to show this, which is talking about ionic compounds. Does that make sense? Because when you do a net ionic equation, it is really easy to see what loses electrons and what gains electrons. Does that make sense? Because you just make the net ionic equation, and then something goes from having no charge to having a charge. Does that make sense? So ionic compounds make it easy to see oxidation and reduction happen. That doesn't mean it's the only place oxidation and reduction happen. You can have reduction and oxidation of nonmetals. So the redox reactions that you've learned so far involve metals. Redox reactions also occur in nonmetals. In an ionic bond, electrons are transferred from a metal to a nonmetal. But in a covalent bond, electrons are what? In covalent bonding, we do what with electrons? Yeah, we share them. Good. And they're not fully transferred. So if you consider, for example, carbon dioxide, the electrons are shared in a double covalent bond. So we would say we have carbon there and oxygen here. In this case, carbon doesn't have those electrons full time. Oxygen doesn't have those electrons full time. They share them. But what we do is we still find it useful to apply sort of an apparent charge on each atom. And the apparent charge is called its oxidation number. Does that make sense? So when we look at carbon dioxide, we look at the electronegativity difference, and we know that which one has a bigger pull on electrons, oxygen or carbon? Yeah, oxygen is more electronegative. In fact, if we drew dipoles on this, we would draw a dipole that way and a dipole that way. Now, as it happens, those cancel each other out, so this thing isn't polar overall, but even still, we can see that the electrons want to spend more time with oxygen. Does that make sense? Okay. So what we say is this. Since oxygen would normally gain 2 electrons to become O2 negative in an ionic compound, we give oxygen the oxidation number -2. And actually, I was going to redraw this nicely down here. We say that, okay, oxygen, if it were to make an ionic compound, would take a charge of -2. This oxygen, if it were to make an ionic compound, would take a charge of -2. But overall, does this thing have a charge? Carbon dioxide charged? No. So it's overall got to be neutral. So if the oxygens are both -2, what must be true about the carbon? Yeah, it must have what we call an oxidation number of +4. Now, this process of assigning oxidation numbers to things is actually not really an exact science. There's just kind of some decision making we make. Does that make sense? It's going to be useful to learn how to do this, but there's just some guidelines, just some kind of rough rules we follow. And I would say I wrote this chart, but I didn't. I stole it shamelessly from the Durham Department of Education. Ah, crap. Oh, it's over. It's all over. Welcome to Chaos Land. Okay. Oh, we are over the rainbow now. We're not in Kansas anymore. My life is fundamentally charmed, which makes it make even less sense how miserable I am. Really, nothing bad has ever happened to me, now that I think about it. Like small little things, but really, as a general rule, I've been pretty lucky. Which is why when my projector goes wonky, I can be like, this is the worst thing that's ever happened to anyone. Sorry? I mean, listen, I assume I dropped out of a heart attack before 40, but until then, I've had it easy. I think, yeah, that's a whole other... I don't know if I've told you this, but my great-grandfather died on the 18th hole of a golfing. Just got a heart attack, just fell over. His favorite thing in the world was golfing. He died golfing. Like, just been gone. And, like, as traumatic as that is for everyone else, I think for him, like, really, you can't ask for much more than that. Does everyone see that this is just randomly scrolling back up? Oh, we're out of control. You know what? It's beach day, and OneNote knows it. And all it wanted was a day at the beach. Is that so much to ask, Orlando? You know, there's only one way to find out. Okay, so here's the rule. Anytime we look at, by the way, this is only for covalent compounds. All right, it is, when you look at an ionic compound, it's easy. You just give it its charge. Does that make sense? So we're only talking about covalent compounds here. And what we do is basically this. Follow these rules in order. And the first thing is this. Any atom that's just by itself and has no charge has an oxidation number of 0. So whether it's sodium, potassium, nitrogen, lithium, oxygen, doesn't matter if it's diatomic, doesn't matter if it's whatever. If it's an atom in an uncombined state, we just give it an oxidation number of 0. Next, ions. So actually, I guess I can erase this because we mentioned ions in the rule. Ions are easy. Whatever their charge is, that's the oxidation number. So if an ion has a charge of +2, its oxidation number is +2. If an ion has a charge of -3, its oxidation number is... Very good. Now, in almost every case, hydrogen is given an oxidation number of +1. The only exception is if it is a metal ionic, if it's with a metal to form an ionic compound, which the hydrides are not very common, but they do exist. So like sodium hydride, magnesium hydride, things like that. In that case, you would have to know that hydrogen is counterbalancing sodium. And because we follow these rules in order, if we know that sodium has a charge of +2 in this case, then hydrogen would have to be -1. You will almost never come across that. As a rule of thumb, if you see hydrogen, you can give it an oxidation number of +1. Okay? And oxygen is almost always -2. There are exceptions, very rare exceptions. What would an exception be? Like some of the polyatomic ions, like nitrate, things like that. It can have a different one. Maybe like hydrogen peroxide, H2O2. It would have a different one. Those are the big ones that come to mind. Oh, it mentions. There you go. So specifically, like in hydrogen peroxide, it's different. But as a rule of thumb, if you see hydrogen, you can say that its oxidation state's +1. If you see oxygen, you can say that it's -2. The metals, even if they're in a covalent compound, which we haven't talked much about metals being in covalent compounds, but that can happen, they follow the rules. And then just remember that in the end, all of the oxidation numbers have to add up to the charge. So if something has no charge, all of the oxidation numbers have to add up to 0. If something has a charge of -1, then the oxidation numbers have to add up to -1. If something had a charge of -4, the oxidation numbers would have to add up to -4. Does that make sense? It's a lot easier to just actually do this stuff, which is why I'm now going to shut up. And we're going to do one example together, and then I'm going to leave you with some homework. Does that make sense? So let's look at lithium nitrate. Lithium nitrate. I want to know what the oxidation number of everything in this is. So let's break it down. If we go back to our first rule, it says the oxidation number of an atom in an uncombined state is always 0. Does that apply here? Do we have any atoms in an uncombined state? No, this is a compound. What's rule 2? Simple ions, right? But this isn't a simple ion, it's a compound, right? So now we have to follow through here. And what we can say is this. The next rule is that with very few exceptions, hydrogen will have a charge of +1. Do we have any hydrogen? No. Okay. Next rule. Oxygen will have a charge of, an oxidation number of -2. So oxygen is going to have -2. And how many of them are there? 3 of them. For a total oxidation number of -6. Okay, next. The oxidation number of group 1 elements is +1. The oxidation number of group 2 elements is +2. Does that apply to anything here? Yeah, what? Lithium. Lithium's in what group? 1. So it must have +1? Yeah. No, she's not. Now, do we have any more rules that mention like nitrogen specifically up here? No, but how can we figure nitrogen out? What does rule 6 tell us? It has to equal 0. So if oxygen has an oxidation number of -2, and there's 3 of them, which brings us to -6, and lithium has an oxidation number of +1, we can determine nitrogen. Nitrogen must balance this to 0. Therefore, what is nitrogen's oxidation number? -5? You got it. Very good. It has an oxidation number of +5 because this thing has to balance out to 0. Does that make sense? Now you might ask, why are we doing this?
Why are we doing this?
What do you mean nobody's asking? I'm asking. Why am I here? The answer is that in our next lesson, we're going to start looking at complex reactions and seeing in that reaction what is oxidized and what is reduced. By the way, for something to be oxidized, what does it have to do? Lose electrons. For something to be reduced, what does it have to do? Gain electrons, because oil rig, kids. Oil rig. Or if you prefer, Leo the Lion says, Okay. It helps to make the hand motion. All right, I left you with some homework. Work your way through it, please. I'm going to attempt to finish marking your tests, and I'm coming right your way. I'm just going to plug this in. Sorry? I'm done up to page 3 on all of them. So for fairness sake, if you must know, whenever I mark a test, I always read everybody's page, like I go through and look, get a sense of how the general thing is. So I sort of have a sense of what's going to be a perfect 6 out of 6 or perfect 3 out of 3, what's going to be a 2, what's going to be a 1. I'm looking for common mistakes. Then I go through and mark them. It's the only fair way. Otherwise, say I mark Blaze's test first, and my expectations are really high. So he gives me an answer, and I'm like, well, that's a 2 out of 6. And then by the end, I'm realizing, oh, lots of people made that mistake. And there's this natural creep that happens where your mind's like, oh, that's a normal mistake. Lots of people are making it. So by the end, you're given that same answer, a 4. Well, that's not fair. Now Blaze is getting marked unfairly just because he happened to be near the top of the pile. That's not cool.
I do like how either way is very bad.
I'm using an example. Blaze hasn't even written the test yet. That's why I picked your assumption. To be encouraged. No problem. So, no, but you can to me. So let's talk through. What are we talking about? Okay. So show me. Forget all the numbers and crap like that. Show me what it would look like if this was dissolved in water. Like just right there. So we take FS. Yeah, and don't even put +1 because the water is just going to be stagnant. Right? Water doesn't actually, like you can put water over there. You know what I mean? Because it's not actually doing it. What do we get? Good. And what should we put? Yeah. What else? Okay, you get like iron metal and sulfur. I mean, what things do you get? You got compounds. Cool. So the reason they're held together is that these are both cool. That's +2. Nice. Now, here's says until these will just dissolve. Until they hit the equilibrium. Right? After which point, nothing more. What I want to know is how many moles like this possibly dissolve in a liter of water before no more. That's the equilibrium. The equilibrium point is when all of this is dissolved. Does that make sense? Make an IC table. And starting with some and you want ending all of this, right? So how this is going to normalize people? You want to start with some of this and end up with you. You want to start with none of this and end up with all, yeah, sure. Obviously, yeah. Now, right, at it's a KQ, right? In this case, it's KSP. Very KSP. By the way, keep in mind, what's the state matter of this? The concentration of solvent? Does that make any sense? Is that going to be part of the KSP? Yeah, so what is it? Yeah, you got it. I wish I could like whistle a tune. I can whistle like.
I can't whistle all of them. Like I can't. I mean,
Do you put like your tongue down below your front teeth?
where am I?
No, like yeah, like that. And then you want like a small gap. And what you have to do is like imagine like not the tip of your tongue, but it's almost like you're trying to push this part of your tongue against your teeth. Put some pressure while you blow. That's better. I can already hear it's better. Now what you want to do is kind of tighten the sides of your cheeks here so that. So yeah, that's the idea. Now you just need, you've got it. Now you just need to bring your mouth so it's got just a tiny little opening like that. So you're going. Oh, you're going. And just the closer you bring your lips together, eventually there's a sweet spot where you get sound. So just bring your lips closer and closer together while keeping pressure on your tongue. There's a little bit there. Did you hear it? I mean, it wasn't much. No, but there was. There was a little. All right, show off. Thank you.
I just want to do it.
What's annoying is I can get a little vibrato in my whistle where I can get no vibrato in my voice. Yeah, see? Yeah, like that's a very nice.
I don't know. All I do is just like I try and play one note for like something like shake.
Just hit the back of your head.
Right.
Well done, Liz. Thanks. Did you get a copy of today's note as well, Blaze? It's got to be somewhere. Where did I put it? It is on one note. Ooh, and I can stop recording.
Oh no.
Sorry?
You gotta hear the whistling.
There you go. What?